All right. Well, good morning, everyone. It's 10:30, so we'll start off with some announcements first. And my name is Angel Weilman. I am a senior research engineer here at Southwest Research Institute. You guys signed up to hear Jim Witte speak, and I'm going to let him start talking in a few minutes. But I wanted to give you a little introduction. This is the first in our new webinar series. We'll be presenting these webinars every 6 to 8 weeks based on holidays and other scheduling. And our topics are going to rotate. So we're going to rotate between flow measurement, fluid dynamics, and multi-phase flow and flow assurance. So please don't unsubscribe from our mailing list. We're trying not to bombard you with emails, but flow measurement topics will come up 2 or 3 times a year based on our schedule. So the next webinar is going to be January 9th, and that will be designing for much higher pressure. That's not gas transmission. That will be high pressure PSI flow loop design. I'll be presenting that. And so if you can join us on January 9th and that's of interest to you, please do. I'll introduce Jim here in a minute, but we plan to have him speak for about an hour. And typically during webinars, questions are held to the end, but Jim would like to encourage people to chime in with questions during the presentation if they have them. If you do have a question, please kindly interrupt with your name and let us know your question. And Jim will answer those questions and then continue on with his presentation. There will also be time for questions at the end. In the meantime, if you're not asking a question, we ask that you please mute your line so that if there's any dogs barking or anything in the background, we don't have the opportunity to hear those. But now I'll introduce Jim. Jim is a staff engineer here at Southwest Research Institute, and he's been in natural gas transmission industry for 37 years now. Most of that time was as a natural gas measurement subject matter expert, and he is actively involved in best practice and standards writing committees such as AGA and API. And some of you may have seen him present at several short courses and schools within the industry. And with that, I'd like to hand it over to Jim and let him do his presentation.
Great. Thank you, Angel. Today's presentation is basics of high-pressure gas measuring and regulating station design. This is intended to be an overview of design practice, and as we look at what we do in the industry, we have a number of metering standards that apply to what we do, but we don't have one overall guideline that says, here's how you build a meter station. So my next slide is my disclaimer slide. And so we're going to focus on some key aspects of meter station design, and what I hope to bring out are places where people commonly make errors or have run into problems in the field that they didn't anticipate that results from design errors. And in the process of doing this, what we want to try to do is to try to define, well, what is a good station design? Then finally, if we were to go into a lot of detail about how to design a facility, this could take hours. And in fact, I have done this in the past when I had done the presentation for company personnel going through company practices. The course went 4 hours, and we still didn't exhaust the topic. So this will be overview, but we certainly encourage questions as we go. As I thought about what goes into defining a good meter station design, I found that there were 4 categories that we need to focus on. The first would be safety. The second would be the functional design. Thirdly, the facility has to be maintenance friendly. And then finally, as most project engineers would say, it has to be cost effective. Usually project engineers are focused on price and schedule, getting the project in. In my career path, I had the opportunity to work as both a project engineer and also work in operations and technical support for operations. So I've had a broad view of all areas of the gas metering picture and meter station design. So I'm going to try to bring out some of the things I've learned. First, we'll talk about safety. We're going to talk about piping design, electrical design, site sizing, location, and security, and some human factors considerations. First, in terms of the piping, of course, we have our DOT standards that drive piping design. Now, I'll point out that the formula that you see on the page here is DOT 49 CFR Part 192 and would be applicable to transmission piping design. If you were a local distribution company, there would be another set of equations that would have, or a different set of design criterion that would limit the design. If you're a producer, you probably are meeting an API standard. And if you're a midstream company, then you would have other considerations that you would meet as well. Typically, meter stations are designed to a 0.5 design factor. And if the facility is located in a Class 4 location, design classes being defined by the number of houses, residences, or large population facilities located within a close proximity of the pipeline, you would derate to 40%. Other things that need to be considered will be drawn out more in this discussion, and that is meter velocities. Some companies are typically designing for maximum velocity between 70 or 80 feet per second for dry gas applications, and some even go as high as 100 feet per second. But they need to be cautioned from the perspective of the gas quality conditions have to be well known. If you have any free liquids or any particulates in the flow stream, you could have an erosion velocity concern that you need to pay attention to, and that particular erosion concern may not necessarily be a function of high velocity. It could be a low velocity concern depending on the piping configuration. I can remember one time where we had a leak in a meter station header where we had some entrained sand in the gas flow. The turbulence in the end cap of the header had stirred the sand, and so we kept sandblasting the internals of the header as we went, until eventually we had a pinhole develop in the header. Typically, when we talk about headers, we're going to try to limit the velocity in that header to something like 30 feet per second or less. And now I wanted to say some things about the meter site itself. Here is a diagram of a layout of a meter station. And what we have here is a filter separator. The piping comes around. We have a meter skid and a regulator skid. Over here we have a control building. This could house a flow computer. This building could also be a chromatograph building. And typically we have some communications equipment, a radio would be common, and then a radio tower situated adjacent to that. The National Electric Code has requirements for assigning hazardous area locations. The close proximity to the piping and the flanges would be classified as Class 1 Div 1, and then there's a radial distance beyond that that's classified as Class 1 Div 2. Over here where this building is situated, that would be an unclassified building. And so there would be no hazardous rating to anything there. Appropriate seals have to be applied in the conduit, though, to isolate between those different hazardous ratings. One thing I wanted to point out about the site, the layout of the site is an important thing. You want the technician to be able to drive into the site. Typically, you want to be able to drive around all of the equipment. So these sites are normally finished with cover stone and such that they can accommodate heavy loads in the yard and get to equipment. One of the things I don't like about this particular layout is that I would have located this control building somewhere over here. This would accommodate running straight runs of conduit in a single ditch instead of having to perhaps run your conduit trenches in a 90-degree turn where you may have to install more conduit. So from a cost perspective, you have some cost savings if you can simplify your layout of your facility. One thing about ingress and egress of the facility, if this is located adjacent to a major highway or a fast lane intersection, you need to have opportunities for the technician to get his vehicle turned around inside the site and headed out in a safe manner. There may be some other considerations that need to be made for that ingress and egress requirement. I've also listed that movement in and out of the site as a human factors consideration. We also need to make sure that the device connections within the facility are made in convenient locations. Oftentimes there is a chromatograph building that's located on site for large capacity stations, and the technicians are required to move calibration gas and helium gas in and out of the building. So there need to be opportunities for lifts or ramps. One thing, if we go back to the site plan here and we look at what might happen here with this particular building, if there's a chromatograph building, you're bringing a hazardous gas into the analyzer room, and you have an analyzer and controller that are two portions of this chromatograph. There is not a particular NEC requirement to address the requirements for that particular build-out in the building. There are many different interpretations of how that is done, though, and each company has their own standard that they apply. Some companies have a single room installation where the chromatograph and controller and flow computer are all in the same room. They say it's unclassified, therefore we don't have to do anything with that. But they also layer in some gas detection and automatic shutoffs on equipment and alarming capabilities. Other companies have the philosophy that they're going to put the gases and the analyzer section in a second room of the building, and they'll make that a Class 1 Division 2 build-out and put the controller on a general purpose side of the building. Some companies are paying attention to the size of the calibration gas bottles and the particular pressure ratings of those bottles. Some are buying the low pressure bottles loaded to a pressure of 250 pounds. Some are buying the high pressure bottles, but the difference between those bottles is the high pressure bottle, when loaded, weighs some 150 pounds. The low pressure bottle weighs about 50 pounds when loaded with gas. So there's a big difference in being able to handle those particular bottles, and you need to consider that. One of those things that's also important is the software that's run in the flow computer. There needs to be a convenient user interface for being able to put the flow computer in test modes and be able to work with your control equipment, moving valves and doing some other things. And I have seen some programs where it was rather difficult to find the pick points to be able to make those selections. Did someone have a question? No? Okay. One of the worst sites that I've found for locating a meter station is to set this in the right of way of a high voltage power line. That's if you can at all avoid that, don't place your meter station at that point. Once upon a time, I knew of a technician who would test a station in such a location. He would have to bring out chains and drape them over the meter tube to ground the tube before he could go to work. That's not a good working environment. Also, if you have relief valves, you don't want those to be placed under the high power voltage line either, or upwind of the high voltage lines, where your gas plume could be blown downstream into the high pressure lines, you know. And getting in and out of the facility, you need an all-weather road. Most technicians drive a truck that's loaded with every tool that they ever bought, and there's a good opportunity for getting stuck if you don't have good conditions. We'll go on to a discussion now of functional equipment sizing. Most companies have sizing tables or programs. When you're sizing facilities, you want to consider the maximum, minimum, and normal flow requirements. Usually this is a maximum at minimum pressure and a minimum at maximum pressure. And you want to design to reduce your uncertainty. A good target is a value that's going to be less than 0.3% overall measurement uncertainty. Of course, this is one of the services we can offer around here is we can assess your facility and tell you what your measurement uncertainty should be for that facility. And then you want to be conservative with where you operate these facilities. Most of your metering error occurs when you're on the bottom end of the range of the meter, or you're on the upper extreme of the meter range. So you want to operate in the sweet spot of the meter. And don't try to do everything with just one meter tube. One of the worst operating conditions is to try to do custody transfer measurement between two pipeline companies, and you have one 30-inch or one 24-inch ultrasonic meter. You're going to have a dispute before very long, and you won't be happy, because you find out that a lot of times that large diameter meter is operating down around 5% of its capacity for about 90% of the time, and then they have a high flow day, and then it's back down again, you know. In the transmission business, on the transmission side, they normally talk in terms of standard daily volume. And if you're sizing on that basis, you need to pay particular attention to city gates where hourly demands can be significantly greater than the peak daily capacity requirement for that station. So that peak demand may be 1.4 to 1.6 times that maximum stated daily rating. One of the big challenges that the industry has had in recent years has been trying to integrate the piping of ultrasonic meters into facilities. The natural gas industry operated for a number of years with orifice meter stations having limited flow ranges per tube. So they tended to be stations in which you had multi-run orifice meters. Then when ultrasonic meters came along, we found that we could size these stations to have an array of tube sizes for the application and accommodate a significant amount of downturn. But one of those considerations, and I hope you can see my cursor moving on the screen, are the end treatments that we put on the ultrasonic meters. And the reason I'm pointing this out is that most of the industry is aware that as gas quality is impacted and ultrasonic meters get dirty, their performance can change. And for that reason, it's good to install some inspection tees so that periodically you can shut in and examine that tube to see if it is getting dirty and how dirty it is in particular. But these tees have caused us some problems integrating the meter tube into the rest of the piping, and we'll be talking about some of that here in just a moment. And in fact, here is an example of an installation where we have an ultrasonic meter. We have the look-in tees on the ends. We could call those clean-out tees. That's a similar term. We have an connecting pipe to an elbow, a lateral turn through block valves on either end, or perhaps a tube switching control valve. And then out the backside, we come off that. We have a 90-degree turn down. And then at the bottom, underground, there's another turn. So if you look at all the turns we're making coming into the entry to that ultrasonic meter tube, we probably have 360 degrees worth of rotation. I hear some discussion on the... Okay. We can hear some discussion on the line. Please mute your line if you're going to have that discussion. Thank you. So I guess the potential problem that would be exhibited with this configuration is you could develop a full body rotation, a swirl, and you have a concern now with the meter type that you select. Will that meter be able to handle that swirl and interpret it correctly in terms of flow velocity, mean flow velocity in that meter tube? Here's an example of an interesting piping configuration. We have a header here that has two mainline feeds coming into it. This elbow and run down to the header. Then we come off with a 4-inch ultrasonic meter and I believe this was a 6 or 8-inch ultrasonic. The concern that I had with this site was that this 4-inch showed extreme turbulence. If we take a look at, and this was the other end of the meter tube. Once again, T's, elbows, close couple, lots of turns. A very noisy situation. But ideally, all of these ultrasonic meters that we install are flow calibrated before they go into service in the field. And what you would like to see is that the diagnostics from the ultrasonics replicate the condition that you had in flow calibration of the meter in the flow lab. So when you get to the field, it should look the same. In this case, this one did not. So there was an inferred bias condition that was causing measurement error. At this point, I want to introduce the concept that we can talk about uncertainty and we can talk about bias. Usually, uncertainty is described as that random variation in your measurement when bias has been removed. But once you have an installation bias, that installation bias is going to be with that facility up until the point in time when you go out and find the source of that bias and eliminate that. It's a very expensive proposition. Here's a look at another meter installation. This has become a very popular type of assembly, and what's popular about this is a skid-mounted meter station where the facility can be constructed entirely in a fab shop. And the good thing is you can have all of your electrical and instrumentation work pre-made, ready run on the skid, and ship it to location, drop it, and make connections to hook it up. It's a very popular thing, but in the process of doing this, I feel like there have been some mistakes made along the way. And one of those is this close coupling of these T's. That is not a preferred method for doing these installations. You end up with some flow distortions that have to be accounted for. And if you're going to build a facility this way, you want to take this entire assembly from this flange at this point to this flange down here and run this in the flow lab and flow calibrate that whole assembly, accounting for the distortions you're getting at these points. The thing you're not accounting for, though, is what happens with the rest of the piping. You've got an elbow going down here. Underneath there is a common center-fed header that links the two meter runs together. And I'll show you in a minute another disturbing opportunity. But this arrangement does not necessarily take into account all possible distortion opportunities if only this segment from here to here is flow count in the lab.
Jim, can I interrupt you with a question?
Yeah.
On the last picture there, do you think that the height of this skid might have been limited by transport capabilities? Or maybe that T could not be higher because it had to be put on a truck?
Yeah. Well, definitely that was a consideration. What I would propose would be a better design, though, is to shorten the skid and end it right here. Drop down off of the T's all the way down directly into the headers, you know. Take your block valve, put it in the vertical position here. You've got a lot of opportunity to fit that valve in that arrangement. And in so doing, you lengthen your riser lengths. You have a lot of opportunity to recover velocity profile on entry to the meter tube, and that's a better situation. And here's one step that approaches that. They attempted to do the same thing by putting their valves in this position. I guess they were able to get about 5 diameters of straight run entry from the header into the meter run. However, it would have still been better had they shortened the skid, dropped the header below ground, and then tied in the riser straight down into that header. If you consider this, though, there's a lot of excavation that's happening on this site as it's being constructed, and putting that header underground is a minimal consideration when you consider that you've already dug a lot of ditch to get to the facility to begin with, and a lot of piping that's going underground. Now, here's an interesting installation. This is the output of an LNG terminal, and we have an overhead header here with a run-up pipe that comes off laterally, an elbow down, and we drop down into a T. We're coming in from above and into this meter run. The interesting thing about this installation is the diagnostic characteristics for these meters were absolutely perfect as compared to the flow calibration condition. And the reason is we have nice long runs of pipe to recover velocity profile. We have a bend, but we have another nice long run before we come into the T. And minimal flow distortion coming into the entry of the meter tube. So think straight runs, long risers. Oh, well, there it is on the next slide. Now, I put in some slides here from Welker Engineering, and I did this because years ago they did these flow studies and captured these visual concepts of what happens with these particular configurations. And it's good to be able to visualize this. You may also do this with some CFD modeling of different piping junctions. But the interesting thing to note here is how flow develops and how mixing might occur or might not occur. Here we have a header with 2 inlet pipes and 3 outlets. But notice that flow divides on the first 2, but the third is not mixed. And I've had numerous people tell me, well, okay, if this was a header, for instance, a compressor station header, you're expanding into this big bottle, it's all going to mix. So if you had 2 different gas qualities coming in, you should get a common quality coming out. But actually the way that works is it's a first in, first out. You see, these 2 gas qualities will be the same, but this one will be typical of this line. Notice that you get some unique flow characteristics when you combine two T's together. So when you have 2 T's combined, you can expect to have a full body rotation coming out up here at the other end. Back to the field example of the meter skid installation. One of the disturbing factors that I find sometimes is how the upstream separation is situated. You really want your run off of your separator to be in direct line with your entry to your meter tube, so that you minimize the number of turns that you have installed before you get to the entry of your meter station. Oftentimes I find that people are aligning the bypass piping straight to the meter tube so that there are multiple turns that occur in and out of the separator before they get to the entry of the meter tube. And that has proven in the field to be a big opportunity for swirl generation. And this particular situation here with the short coupled T's, double T's, and that situation does not eliminate that swirl concern. In fact, in some cases, it accelerates the swirl. Headers. We have different ways that we can do headers. We can build a T header, a Z header, or a U header. Back in the 80s, there was a study done that showed that the U header would give you the best balance across the station. In my experience, we always built as a Z header because we knew we would have an imbalance, and we always made the run at the end of the inlet header the primary run on purpose because we knew it would max out first, and we were applying cascading tube switching such that this would be tube 1, tube 2, tube 3, and as we switched, we were always keying off of the flow rate on the previous run so that we would max out the entire station before we would overrange a meter tube. One thing I want to point out, this is an important little consideration. This note, 2 nominal pipe diameters between the T and the end cap on this header. If you don't have that opportunity there to move that turbulent junction of the end cap away from that T, you'll find that your runs 2 and 3 will have greater flow than the primary run. So it's one of the finer points, but it's one of the things you want to pay attention to, and it's one of those things that I most commonly find people make that mistake. They will weld that weld cap right on the T. This is a picture of a mainline regulator installation. We have a regulator and overpressure monitor. You want to target your sizing for 10 to 90% of valve travel, such that you're always operating in this range above 10% and below 90% of capacity of that valve. In this installation, we have pilot heaters, we have pressure pilots that are pneumatic devices that are controlling the throttling of the control valves. Also, the other consideration about this skid was this was a location where the MLP of the pipelines had changed, and this facility was used to protect that downstream segment of piping that was the lower pressure rating. But it was also receiving gas from the shale plays here in South Texas, from the Eagle Ford Shale, and they had free liquids going through that. The next thing I want to point out is gas quality and merchantability. So I mentioned the free liquids going through that particular facility. They had actually intended for that to occur because just downstream of this location was a processing plant where they were separating liquids and processing the remaining heavies out of the gas. But if that was not your intent, you certainly need to pay attention to gas quality and what would impact gas quality. Usually when you're doing an interconnect, you have certain tariff requirements that control what it is that you can do. And here is an example of one operating company's tariff criterion with, H2S limited to a quarter grain per 100, water vapor limited to 7 pounds per million, CO2 3%, oxygen 0.2%. A gross heating value 1100 BTU, minimum of 967. This would be an important consideration if you're a midstream company and you're doing processing, to stay within those heating value limits on what is returned to the pipeline. Typically, operating temperature is limited to 120 degrees Fahrenheit. I had some experience where we had some offshore sites where we actually allowed the maximum temperature to go up to 130. But this causes some particular special considerations with personnel handling equipment around the line if it's getting that hot, And then total sulfur, this was 20 grains per 100. That's a lot. That's a lot of total sulfur, I think. But, okay. So all of these need to be considered. And then in particular, each composition of gases you look at is going to have a different characteristic in terms of phase envelope. And there are 4 different gases here. There's Amarillo gas, which has a high nitrogen content, not such so many heavies. Gulf Coast, which is pretty lean. Wyoming was a very rich gas, and then the South Louisiana gas was very rich as well. And you can see as we increase the number of heavy hydrocarbons in the gas mixture, we end up having a higher cricondotherm. Cricondotherm is the highest temperature point on the phase envelope. Here's another look at a phase envelope. And in this case, we're looking at the phase envelope for this particular composition of gas. And I've included some water saturation curves on the plot, and you can see that water saturation is a completely different consideration from hydrocarbon dew point. Water dew point, and then also here's a hydrate formation curve. Particular points of interest would be where this hydrate formation curve crosses each of these saturation points, and you have opportunities for hydrate formation. And you can see that these hydrates could form considerably before you get to a freezing point of water. There's a lot more discussion that could go along with that consideration, and I just wanted to mention that there. Other things that go into facilities these days, most of the facilities that are being installed now have a high degree of automation associated with them. They have automatic tube switching. They have flow control or pressure control. And they're doing online sampling and analysis, maybe overpressure protection. And you still have some fundamentals that you have to pay attention to, though. Where are you going to locate your gas sampling points? How are you going to sample? Your sample probe should be installed in the middle third of the pipe is conventional practice. You want to install probes with heating to prevent condensation of liquids in your gas sample. And you want to insulate that installation so that you don't have any effects from wind or ambient conditions that would change phase. Another important consideration for meter stations is what do you do for gas processing? In particular, filtration and separation is an important concern. Over here on the left is a picture of a person changing filter separators in a mainline filter separator. Here's an installation of a city gate with a small filter separator. In fact, this was a turbine meter housed in this house. And here's an odorization assembly that's a part of that meter setting. If you don't pay attention to filtration, though, and these other things, you get conditions like this. When your meter tube looks like this on the inside, you're most definitely going to be measuring an error. And you will meter an error until you discover that you're dirty and you clean it up. So the use of the filter separators upstream of the measurement is an excellent idea. And there's more. More things that we should consider. We need to consider failure modes, alarming. What are you going to alarm? What warnings will you set? What types of communications are you going to use? Here we see a platform. This was located on a large lake in South Louisiana. And one of the concerns I had about this site was how high this meter setting was from the water. It looks like during stormy conditions, this thing could actually go underwater. One of those other things you want to consider is gas property updates. How often are you going to update gas properties? Do you have a chromatograph? You probably wouldn't set a chromatograph in this installation. You would probably do either composite sampling or spot sampling. But there's a question about, well, how often do you apply those gas properties? And getting that in sync with your other flow measurement is a particular problem. A lot of companies will do a post-processing of that data and recalculate the data that's coming from the gas flow computer using the latest properties from that gas sample. In an environment like this, where we have this platform, power requirements are a particular concern. Certainly this equipment is all battery operated, charged with solar panels, And in an offshore environment, you want to have about 21 days of battery autonomy. Usually in 21 days in the winter in particular is when offshore it becomes very cloudy. Usually there's a time in there where you can get a few days of charge time in. However, I can recall some times where we had bad weather continuously for about 2 months, and we were flying the helicopters out, changing out batteries and charging batteries and such. And these are things that are routinely dealt with on the pipeline. Other control considerations are, as I pointed out earlier, might be odorization. If we look at failure modes, you would want to classify the facility and how you're going to fail equipment depending on the application. If it's a power plant, you consider one thing. Mainline is a unique case. City gates, pipeline to pipeline interconnects, or receipts from gas storage. All of these could have different considerations. I will point out for your overpressure protection, typically you're wanting to make sure that at all costs that fails in a closed condition, such that you're always failing safe. However, in this one particular instance here with the mainline pressure limiting station, the last thing you really want to do is to fail your mainline off. So you have a difficult situation qualifying how you fail that particular overpressure application. A lot of times they will fail in last position. For the design engineer, it's very important to produce a piping and instrument diagram. And with that, put as much detail as you can into that drawing, because it's a tool that's used to communicate how is this facility going to be operated. Usually the design engineer designs the project, the construction guys get it, they go build the facility, and the measurement technician comes along and he's got to place it in service and start it up. How does he know what to do with the operation of that facility unless you tell him within the plans for the station? As I mentioned earlier, most of the industry is using gas flow computers, and this diagram shows the control options that you could have for your gas flow computer. You can do a flow control. You can do a decatherm or energy control. You could do a pressure control, or you could interact the two here through a selector function and have a flow control with a pressure override, or a pressure control with a flow override, or any other combinations that are allowable within the design scheme. If you are if you're a single source supply to a power plant, your control method is pressure control. You're going to feed that plant. You never want it to run out of gas, and you're going to maintain pressure. If you're the third supply to that plant, someone else is the primary or the swing, they're going to be on pressure control. You're going to be on flow control. But it's important that for your project, you know how you interface with the other suppliers to that same plant header. These are all things that need to be considered. The meter station needs to be maintenance friendly, and some of these are considerations of being maintenance friendly. This picture was taken of transmitters installed on a platform in South Louisiana, and I was standing under the transmitters, taking the picture of the transmitters overhead. In order to service these transmitters, they had to build a catwalk for the technician to lug his test equipment up
to this location and test those transmitters. So accessibility of components is a major consideration. You've got to plan for in-service maintenance, so you've got to be able to take things out of service and work on them. And assembly and disassembly is an important thing. If you need to clean meter tubes, you need to be able to take these out of service and do cleaning, which requires some disassembly. And then if possible, you want to reduce your painted surface area because that's another maintenance item, and provide shelter for the equipment and the operator. Here is a picture of an offshore platform. There's a Bocal helicopter on the platform behind it. If we think in terms of cost-effective designs, we want to produce optimum results for the expenditure. So for this consideration on our offshore platform where you're spending about $1,200 per hour to fly a helicopter out to this location, when you get here with the technician, he wants to immediately be able to go to work. And it would be nice if you had adequate shelter for him to be able to do his work on the equipment. In this case, the shelter is right over here. There are gauge lines running in, and all the transmitters and flow computer are located in this building. Some factors that go into cost effectiveness are maintenance costs, frequency of call-outs. You know, it's nice if you save money putting in this single run orifice meter station, but if you have to go out and continuously be changing plates to meet the demand, then it's not such a good thing, and that doesn't accommodate autonomous operation. So that needs to be considered. Oftentimes what we get in terms of definition from the deal makers and instructions to the engineers don't fit well with that particular concept. And then it needs to be appropriately assigned for the application. If you're constantly operating on the bottom 10% of capacity, you're never going to get good measurement results, and you're likely to have arguments with your customers. Now here's the shameless slurry plug. But seriously, I wanted to introduce some services that Southwest is offering now. We can do meter facility design reviews and recommendations, loss and unaccounted for gas resolution, either as a single pipeline or as a total system. We can do some advanced problem solving for you. We have experience with LNG terminal material balance and non-traditional gas blending. We do meter audits. We can do a third-party impartial audit of your facility and give you a nice report for you to discuss with your customer, and do an uncertainty assessment of your facility. And then we also can take on special projects related to policy and practice, industry surveys, or root cause analysis support, technical support for your root cause analysis. With that, do we have any questions? Do we have anyone left on the line?
We do, and thank you for the presentation, Jim. Now people can type up with their questions. If you feel that your question is not going to be able to be answered during this meeting, or you have a more specific question, Jim's information is on the board or on the presentation here, so feel free to contact him after the meeting as well. Okay, do we have any questions? I guess I have a question, Jim.
Oh, okay.
Is there a rule of thumb for like a minimum flow rate that should be measurable? Let's say the flow meter company says this is good, up to 0 to 100%. What's the rule of thumb for the minimum?
there's not a rule of thumb answer for that, but I'll qualify it. Usually the deciding factor in my mind is what's happening with the minimum velocity in that tube and the ability to accurately measure temperature in that run. So if you get too slow in the meter tube, you have more ambient effects, and you'll bias your measurement, in particular by introducing temperature measurement errors. But also at certain minimums, like 1 to 2 feet per second, you don't produce a stable velocity profile. It's always turbulently changing, and so that in my mind would be a place that you would want to avoid in terms of trying to produce high quality flow measurement.
Thank you.
So is Eric Rigdon still online?
I don't know. Yes, he is.
I'm still here.
Hey, Eric, I saw that you had joined the webinar, and I appreciate you supporting us this way.
Yeah,
Thank you for joining.
Thank you.
Does it bring back memories of the past?
Yes, and some stuff that I didn't know about too. So very good stuff.
Thank you.
Okay, well, if we don't have any other questions, I'd like to thank everyone for joining us. You might get one more email from us asking for some feedback. This is our first in a series of webinars, so we would like to know if there's things that can improve and what you guys enjoyed about it. So thank you very much.